and missions pilot for Reno Composite Squadron, Civil Air Patrol. So last year, 2 years ago when we had IWAWS, we decided we had to have him back for future IWAWS sessions, and we kind of said the same thing this year, one of our favorite speakers. Sandy, I do have your PowerPoint on. You want to do a quick audio check?
How do you hear me?
Yes. We can hear you. Everything looks good on my end, too.
Great. So you got the video up as well?
We do.
Yep.
Wow, it's actually working today. After yesterday's difficulties, well, I switched laptops. This one should work a little bit better. So, welcome everyone. I don't mind bringing up the rear on this one. I hope you find it fun and interesting, a little something different from what everybody else has been talking about. But the irony of it is it all kind of ties together. One of the things Dawn Johnson was helping me with when I was working on my instrument rating, she was my go-to person for helping me learn a few details prior to taking the FAA exam. And we got to chatting and realized how many things are very similar in the weather between what I look at as a fire behavior analyst out on forest fires and what I look at as a pilot. And so we thought it might be kind of interesting to put it together and do a comparison of the two. And for a lot of people, we learn by comparing one thing to another. And that's the way I learn, is if I can compare back to something I already know, it helps kind of stick. And so when I kept referring back to my fire knowledge and experience, learning the aviation component of it really tied in together. So we thought it'd be kind of fun to look at it from a different perspective. So anyway, as she said, I was with Reno Fire. I do most of my side job from the main job is going out with incident management teams on special assignment. I've been on forest fires in 9 western states and worked as a fire behavior analyst. What does a fire behavior analyst do? We work on fires for food, camp food. Sometimes it's pretty good, sometimes not so much. 2 fires down in Southern California a couple of years ago, I gained 5 pounds each fire. That was not a good thing. Anyway, what I fly, as was also mentioned in the previous part, is I have my airplane single engine land and sea ratings, instrument rating in about 800 hours. I've gotten to fly up in Alaska. That's where I got my seaplane rating and flew Super Cubs up there a little bit. I fly pilots and PAWS, which is an awful lot of fun. This was my very first airplane in 1946 in Ronkonkoma. Landed on the beach at Pyramid Lake. And this is my 74 Beach Sundowner in the upper left that I keep at Reno Airport. I fly with the Hayward Air Rally, which if you've never looked at it before, look it up. If you're a pilot, you'll find it to be a total hoot. Civil Air Patrol, I fly with them. I'm the Emergency Services Officer, Safety Officer, and a mission pilot. And this is my daughter and me in a fly-in in Columbia, California for Father's Day. She was pretty bummed this year. She goes in a text the other day, well, I guess this means no Father's Day fly-ins this year. Unfortunately, no, but hopefully in the near future. And one of my biggest kicks I get out of flying, in addition to flying pilots and PAWS, is to fly kids with the EAA chapter doing Young Eagles. So if any of you want to get involved in other activities in your aviation, there's a variety of different things, and I seem to have gotten sucked in eyeballs deep since I got back into flying. I hadn't flown in 28 years. Right around the time I retired from the fire department full-time, I ended up getting back into flying, and boy, did I get into it in a big way. So anyway, as a fire behavior analyst, we look at fire behavior as having 3 main components: fuels, topography, and weather. Anything that burns is the fuel. Obviously, topography varies over space, not much over time, but the fire does burn across different geographic features. But the most dynamic feature of fire behavior over space and time is the weather. And that's why when we go out on these forest fires, we have not only the fire behavior analysts, but we have what are called IMETs, or incident meteorologists, who come help us out on our incidents. They don't help us out. They're one of the key players for predicting fire behavior and fire spread. The meteorologist and I are glued at the hip, and we work together jointly to come up with a plan, and then we brief both the firefighters and the fire incident managers when they plan how they're going to fight the fire. So there's 2 primary things that we look at as fire behavior analysts: flame length and rate of spread. Flame length we use for 2 things: size of our safety zones. If we have to disengage, the conditions are getting poor, we want to move back to a safety zone. So we have to predict what the intensity of the fire is going to be if things get worse and base the size of the safety zone on those worst conditions. Second thing we use it for is tactics. What kind and type of resources do we need? And we use this little chart called the hauling chart. If you notice on the lower left, the bottom curve, a little guy with hand tools. So from flame lengths of 0 to 4 feet on this chart, see 4-foot flame length, we can attack that with a hand crew. If it's 4 to 8 feet, we use heavy equipment and engines. 8 to 11 feet, fire has the potential for crown fire and more intense. We have to use aircraft, things like that. Over 11 feet, according to the textbook, attack at the front of the fire is ineffective. In simplest terms, we call it 0 to 4 haul tools, 4 to 8 haul water, 8 to 11 haul retardant, over 11 haul ass. You don't want to be there. Fire behavior rate of spread is the second thing that we look at, and we use it for two things as well. We look at both escape routes and what overall strategy we're going to use for the fire. Escape routes are important because that's how we get to the safety zone. The problem is if the rate of spread increases and is now faster than we can run, we won't make it to the safety zone. And as I tell my fire students, if it can catch you, it can kill you. So you definitely want to make sure that you can predict spread rate, or in this case, spread time. Compare that to the time it's going to take you to utilize your escape route and get back to the safety zone. So that's a really important thing for us to know, and we have to do some simple calculations even out on the fire line. You don't need a fire behavior analyst to help you figure out changes in spread time and whether your escape route is effective. The second thing we look at is the strategy. Strategy is the number of resources that we're going to use. We base that on the number of acres burned and primarily on the perimeter. Acres burned is what we tell the news media because that's what people can relate to. We're concerned with the perimeter because that's where we're actually fighting the fire. So the acreage is not as important to us as perimeter is. So the other thing that I do as a fire behavior analyst is I predict the potential for. I cannot predict when or how, but I can make reasonable predictions of the possibility of certain kinds of extreme fire behavior. Things like torching and crown fire, fire whirls, extreme rates of spread, wind events, which basically drive the extreme rates of spread, prolific spotting, plume-dominated fire behavior. So let's take a look at it. I like to use the little phrase like the movie weather actually is all around us. When we look at it from that perspective, some of the things that affect us as firefighters as well as pilots is the wind. As we just had in the last few modules, some outstanding discussion about the wind and wind factors, both wave activity, low-level wind shear, and other things like that. The wind is of great importance to us as firefighters, just as much as it is to pilots. So those last couple of modules that we covered were really excellent information, and I wish firefighters could pay attention to it. It's not just for pilots, it's for us firefighters as well. So anyway, we also look at things like atmospheric stability, which we also talked about, convection and turbulence. For pilots, we look at the kind of cloud formation because cloud coverage and the type of clouds has a lot of impact on our fires. We look at frontal activity, primarily cold fronts, and most importantly, from those winds. We look at precipitation and the effect it has on fuels, temperature, dew point, and relative humidity effects. All of these things play into fire behavior. And finally, thunderstorms. So first off, let's talk about the wind. General winds created by high and low pressure areas, as has already been discussed and most of you already know. And it's those winds that are generalized winds, which we in the firefighting business refer to as general winds, prevailing winds, winds aloft, or ridge-top winds. Sometimes those winds can surface and become a real issue for us as firefighters. Also created by the areas of high and low pressure, as you can see on this graph, is a jet stream. And even though the jet stream's way the heck up there, 30, 40,000 feet or more, it can have an effect on our fire behavior. For example, when a jet stream goes directly over the area, it creates atmospheric instability, and this divergence, as you see in the graph, creates a lifting mechanism, sort of like the top of the wing of an airplane, and it enhances vertical growth of the smoke column. And when it does that, it increases our potential for an extreme fire behavior condition called plume-dominated fire. So jet stream passing over the top of us is definitely an issue of concern for firefighters. We had a great discussion and presentation both yesterday and today on the effect of wave type clouds and mountain wave winds. Resists vertical movement, but we do get those vertical waves that can cause some dramatic effects. For us down at ground level, our biggest concern, just like a pilot is on the lee side, we get those rotors. And those lee side rotors and turbulence, as you can see in the right-hand graph, those things are what's going to mess with our fire big time. I cannot predict where the fire is going to go. We're on the lee side of a mountain like that, we start getting mountain wave winds. If we see those lenticular clouds starting to form across the valley floor just east of the Sierras here outside of Reno or over Reno, when we start seeing those lenticular forming in the morning, hold on to your shorts, boys and girls. We know it's going to get windy at the Earth's surface by afternoon. And that's when we get the low-level winds here at the airport, we get the lee side rotors, and then we get wind events which cause extreme rates of spread. So mountain waves, we see those form. Number one, it's bad for pilots, but number two, it's going to be bad for us if we have a wildland fire burning down on the Earth's surface. So it's an issue of concern for both pilots and firefighters. Here's an example of a low-level surfacing wind and the high rates of spread that you can see. That's 4 to 5 foot deep sagebrush. Those are 50 to 60 foot long flame lengths. We get fire whirls at the head. We're getting short-range spotting out ahead, as you can see. I have no idea what the helicopter's doing, but I do know those firefighters are going, we don't want to be here, and they're hightailing it out of the area. That is when the fire behavior is so extreme, it is resistant to any kind of fire suppression activity. That's when we just plain get the heck out of the way, let Mother Nature do its thing, and then we go back and catch it when conditions are more favorable. And that's where the meteorologists and I come in and say, here's when it's going to get better, and when we can take tactical advantage of improving conditions. So the other kind of wind that we deal with is called local winds, and this is created by solar radiation heating the Earth's surface in the daytime and radiant energy back out into space on a clear sky night, creating downslope winds. So the solar radiation heats the Earth's surface, the Earth's surface warms the air in contact with it, and that warm air rises, creating upslope winds. Later in the day, those upslope winds combine to create up valley winds. Now, as pilots, we learn to fly in those convective up currents on the slopes. Sunny slopes have upflow winds, and those are good for sailplanes and any kind of flying in mountainous terrain. You don't want to be on the downwind side of a canyon or valley. You always want to fly the upwind side so that the updrafts up the slope are the ones that are going to lift you up and give you improved performance. But what about us for firefighters? Well, early in the day, as soon as the winds pick up and start going vertically up slope, guess what direction the fire is going to spread? Slope has an effect to make fire burn uphill, but wind combined with it will make the fire spread much more fast, much more quickly. There we go, better grammar. But later in the day, as you see the upslope winds convert to up canyon, that's a 90-degree wind shift for us on a fire there mid-slope. And that means low-intensity fire on the flank suddenly becomes high-intensity head fire, right where we're trying to work, and the fire can burn us over. So we need to be able to predict when those upslope winds start to become up canyon, and we build that into our firefighting plan. Everything in firefighting is about time and timing. And we look for when we can take tactical advantage of these kind of conditions and when those conditions are going to shift. Now, at nighttime, we start getting cooling, radiant cooling as radiant energy goes back out into space as long as it's clear sky. And we start to develop downslope winds. Well, that's 180 degrees off from what we had during the day. So now guess what direction the fire is going to burn? It's going to burn downslope. And then by early morning, downslope winds combine to create down valley winds. And now we've got a 360-degree shift in fire spread. Morning, it's going upslope. Mid to late day, it's going across slope. Nighttime, it's going down. And then early morning, it's going the exact opposite direction down canyon. And that's how we have to try and predict where this stupid fire is going to go so we can catch it. And as you're flying in these conditions, it also makes a dramatic difference in how we approach the topography. Flying in mountainous terrain, this is one of the driving factors that makes it really important to be able to know good mountain flying skills. Now, wind is the horizontal movement. The other thing that we look at is called stability. That's the vertical motion of air. Stable air has a tendency to want to settle and move downward. Unstable air enhances vertical motion of an air mass. I prefer to call them blobs of air. That's a technical term. And so you got a blob of air, and if it wants to go vertical, that's an unstable atmosphere. And if that blob of air's got moisture in it and it goes vertical, it could potentially start creating thunderstorms. And in a moment, we'll talk about plume-dominated fire behavior. So anyway, unstable atmosphere promotes vertical growth. Guess what that does to the smoke column on my fire? It makes that smoke column stand up vertical, and there's all kinds of things that can happen from that. Active burning of the fire overall, well-developed winds at the base of the fire. Good vertical smoke column can transport burning embers long distances and cause long-range spotting. And we have the potential for plume-dominated fire, where the fire controls the environment. I'll talk about that in a moment. Unstable atmosphere at the surface is useful for pilots if you're in a glider, as was mentioned and discussed previously. If you're in a little motorized aircraft, you're going to get the snot out of you, let's be honest. So where do we want to go? We want to go higher up so that we get a little bit smoother air, less convection, and it's a little bit smoother ride if you're on a cross-country flight. But when you got to fly at lower altitudes, like when I'm doing a Civil Air Patrol search, we're 1,000 feet off the ground. And on a warm summer day, we're getting beat up big time. Here we are, 10 degrees flaps, 90 knots, cruise along in a 206 or a 182, looking out the windows with a crew of 3 or 4, and we're all sitting there going, I don't feel so good. And that's all because of solar radiation heat in the Earth's surface and causing this convection and low-level atmospheric instability. So we get those thermals, great for the gliders, not so good for the rest of us. Anyway, this is how a fire can develop both from surface low-level inversion into a low-level event, and then gradually progresses throughout the day. I've seen this graph before. I think I've heard the terms called a skew T. Maybe I should take a class and learn what this thing is. Anyway, here we are, first thing in the morning. We have a pretty solid inversion. The temperature is actually getting warmer as we go up in altitude, and that means that it resists vertical movement of the air. The smoke goes up just a little bit from our fire, and then it kind of flattens out. We get a little bit later in the morning, and now it's warming up a little bit more, and now the inversion is starting to break. It's starting to mix out. And as it does that, the cold air down at the Earth's surface is starting to warm up because of solar radiation heating the Earth's surface. And that's when we start getting that surface convection that we saw on the previous slide. Now, as we start working a little bit later in the morning, the inversion has fully broken, and now we have the air starting to cool rapidly as we go up in altitude. Well, the smoke is warmer, and the air around it is cooler. That smoke column is going to continue to go vertically and produce a well-developed convective column of smoke. By the time we hit 2 o'clock in the afternoon or thereabouts, we're at the peak heat of the day. We're at the peak of the burn period, 2 to 6 p.m., right in that window when our most active fire behavior occurs, and that's when things start getting really rambunctious. And it makes it more active fire, so it's difficult for us to get near it, and it makes for a lot more unstable atmosphere and more difficult for firefighting aircraft to work because they're getting the crap beat out of them too. So anyway, here's the mixing height where we start to hit another inversion aloft, and that caps off the smoke column. Low-level atmospheric stability we typically see as either fire whorls in the fire or dust devils. Now, the black area of the fire itself absorbs a huge amount of solar radiation. And when it does that, it causes really strong surface instability and convection, which then can cause dust devils right within the fire area. But if the fire isn't completely out and cold, we run into this problem from the Moss fire. It's a perfect example. You notice that dust devil of ash and hot gases rising. Well, mixed in there somewhere, guess what? We had some burning embers. And now, just when we thought we had that fire contained, we got a line around it, got hand crews on it, got engines running, helicopters and air tankers, yada, yada. Baby, we got this one. We're going home tonight. Whoops, I guess not. And then we got to rekindle outside the fire line. This one actually ended up running almost double its original size. And that was not exactly one of our favorite days. So what happens when the incident meteorologist and the fire behavior analyst talk about the wind? This is when we had a transition between IMET's fire I was on up in Oregon about 20 years ago. Frederick Bunod dropped out of medical school to become a meteorologist. Amazing, brilliant man. And he and I are still friends and stay in contact to this day. He lives up in Oregon, now recently retired. This is Rob. Rob is from Colorado, I believe, and he was my IMET for the next 2 weeks when Frederick left. And this young lady here was both a helicopter manager and a trainee fire behavior analyst, so she was working with me for most of that 3 weeks I was on the incident. So we're sitting in camp one day, and we're all sitting around in our little yurt, the metal framed tent, going, well, interesting day, and somebody sticks their head through the door and says, what do you think the wind's going to do today? Right about that moment, we got a little wind and fire camp, and our 20-foot diameter yurt decided to go airborne, and it went vertical, and it went probably 50, 60 feet up in the air. Somebody in fire camp actually had a camera and caught this picture. I said, give me your camera, I'll pay to develop your pictures. So I was able to get that copy of the picture as it happened. And so as we're looking at it, we're going, okay, what could have caused this? Well, I think we figured it out. You know, you're sitting there going, okay, what could have caused this kind of event? Well, it's pretty easy to note. Obviously, it was UFOs, right? See, there's one right there. Visual evidence right there. And we saw this guy walking around fire camp the night before, so that led us to some suspicions. And then when these two guys showed up, and they kept trying to tell us that what we actually saw was a reflection of Venus off a weather balloon into some swamp gas, I don't think I believed that story. So I'm still convinced that it was UFOs. This is where our yurt used to be over here on the left. You can see the patch in the ground. And this is what they gave us afterwards. It was quite an entertaining little experience. Anyway, as we look at stable and unstable conditions, pilots look at the same thing that we firefighters do. Do we have stable conditions? Well, down low near the fire, we're going to have low fire intensity. We're going to have poor visibility because the smoke is just hanging in the valley under the inversion. You're going to have potentially fog. You're going to have flat stratus clouds. And as was described about the mountain wave effect, one of the conditions needed to create those mountain waves is resistance to vertical movement or stable atmosphere. So stable air we can recognize by having mountain wave clouds. But what about in the morning when we start heating up the Earth's surface? As mentioned, the inversion can break. The Earth's surface warms up, we start getting convection lift. This cap right here on top of the inversion either goes away or moves way up. And now we start having more active fire. We start seeing clearer visibility, gustier winds, good smoke dispersal and visibility. And one of the biggest things that we look for is clouds going vertical, not flat clouds, vertical clouds. And when we see those, we start getting nervous because of the potential of creating thunderstorms. But the same mechanism that creates thunderstorms is what also creates plume-dominated fire. So what are clouds? Clouds are nothing more than visible droplets of water. Up here we see some happy little clouds. You guys remember that guy? I used to love watching this show. Anyway, any cloud touches the ground is fog, zero visibility, we're below IMC, we can't fly. That's good for firefighters, though, because it really raises the moisture content in the fuels, and the fuel doesn't burn very well. So fog is a good thing for firefighting, bad for flying. So anyway, we classify clouds by their appearance and how far above the ground they are. Here's some of the different altitudes, as you guys are probably familiar with. Some of the clouds you guys probably already know from your flight training. Low-level stratus clouds, stratocumulus that don't go vertical. Went dancing through those in one of the CAP aircraft about a week ago. We had a airborne radio relay mission that we were practicing, and the tops of the clouds were right where my flight level was. So we're cruising in between the stratocumulus clouds at about 11,000. It was pretty awesome. So anyway, we start seeing towering cumulus, we get nervous. Altocumulus castellanus, again, we start worrying about that vertical development and the potential for thunderstorms. And when we see the real high-level clouds, that may be potentially an indication of an approaching frontal system, which we're also concerned with. Okay, some of the clouds to recognize: cumulonimbus. Among us firefighters, we refer to this as cumulo-overtimeness. cumulo overtime clouds because when they start lighting off lightning fires, we ain't going home that day. We are going to be there for the duration until all the fires are put out, and sometimes a lightning bust can light upwards of 1,500 fires, and trying to chase them all can be a real challenge. Cirrostratus, kind of pretty easy to look at. One of our local meteorologists on the news years ago used to call them high, thin wispies. I always thought that was pretty cool. Anyway, alto cumulocastellanus or ACUS, these are an indicator to us of two of the three things that we need for development of thunderstorms. We have moisture because there's clouds visible, and they're already starting to go vertical, which means unstable atmosphere. The only thing missing is a lifting mechanism, and guess what causes that? Sunshine heats the Earth's surface. We need a lifting mechanism, and those can develop into thunderstorms. And so that is what we want to look at as pilots, as well as us firefighters. These are altocumulus flockus, supposedly looking like a flock of sheep. We're more concerned with this because of shading. If we have minimal shading, it means the surface of the Earth and the fuels are going to be hotter and burn better. But if we have a higher amount of cloud cover, it actually shades our fuels, decreases the amount of burning and the intensity of the burning because there's less solar radiation. So we like high cloud covers of altocumulus flockus. Good stuff. More than 50%, we're smiling because that's going to really help decrease the intensity of the fire. And then, of course, it's already been covered. We talk about the lenticulars. I don't talk on my cell phone when I'm driving down the highway. No, I lean out the window and take pictures of clouds. This is driving up north on the freeway, just south of Reno, because we get some of the most awesome-looking lenticulars around here, and I just love taking pictures of clouds. This is Black Butte outside of Bend, Oregon, Sisters, Oregon, actually. And after flying past for 2-3 weeks, the end of the fire assignment, I actually had some free time to go and hike to the top of it. That was pretty fun. Okay, this is also what we refer to as fog. Below IMC conditions, visibility is too poor to fly, but we firefighters, we smile because it brings the moisture content of our fuels up. Fire goes out. That's always a good thing. So what's good for the pilots is good for the firefighters, not necessarily good for the pilots. And I like when I'm taking pictures of cool-looking clouds. This one was in my neighborhood a couple of years ago. I took the picture, and then I saw a couple of these, just thought they were kind of funny. So anyway, there's some fun-looking clouds. Now let's talk about extreme fire behavior. Extreme fire behavior goes into several different factors. Some of the things that contribute to extreme fire behavior: obviously wind. Available fuels. That means even though the fuels are there, like sagebrush, there may be too much moisture in the foliage for it to burn, so it's not available to burn. But later in the season, as the vegetation starts going dormant, fuel moistures drop, and it makes them more available. Now, what about dead fuels? Dead fuels are daily driven based on cloud cover, temperature, relative humidity, dew point, and those kinds of things. So we look at temperature, dew point, relative humidity relationships as pilots. Well, we look very closely at that as firefighters because it directly influences the ability of the fuels to burn, and that's real important to us. And then finally, the other thing that we look at and have discussed in great detail is the unstable atmosphere. So when we talk about wind, there's three things that we're most concerned with winds, and that's frontal winds, specifically cold fronts, foehn or föhn winds, depending on which meteorologist and which definition on the internet you read, and thunderstorm outflow winds. If it's a wind event like a surfacing mountain wave, we're going to get a very strong push, and the fire spreads in a long, skinny stretch. You know, it's easy for me because I know exactly what direction it's going. Now all I got to do is calculate how far it's going to go before the wind dies down, and that's where I get my work with meteorologists. Wind-driven events are actually, in some ways, pretty simple to predict fire behavior because it's a fairly known quantity, and I can model this very easily with fire behavior modeling software, but not when it's plume-dominated. We'll talk about that in a moment. Cold fronts are a great concern to us because, as you can see, initially we have a fire with light winds out of the southeast. As a cold front approaches, our strongest winds are going to be right here at the frontal boundary. So we got a fire moving out of the southwest towards the northeast, right in front of the cold front. But as the cold front boundary crosses the fire, it then causes as much as a 90-degree wind shift. And that means that what used to be flank fire of lower intensity down here is now all head fire. And that's when we have to beat feet and get the heck out of there because it's going to burn us over if we stick around. And sadly and unfortunately, it is this kind of fire behavior and frontal activity that has caused multiple burnovers, fatalities, entrapments, etc. This is a big deal for firefighters. It should also be a big deal for pilots because of the dramatic kinds of wind shifts and wind shear that are associated with it. In addition, cold fronts can also develop some pretty dramatic thunderstorms right along the frontal boundary, and that can create downdrafts and other problems as well. So cold fronts are a really big deal to firefighters, and as most of you as pilots know, it's a big deal for us too. Now, the other thing we talked about are called foehn or föhn winds. Föhn winds where you got a big blob of cold, high, dense air sitting on one side of a mountain range, kind of like filling up the punch bowl with dense, cooler air, high pressure. And it slops over the ridge of the punch bowl, starts to flow down the other side, and adiabatic heating occurs because we're compressing it. As it goes down in altitude, atmospheric pressure increases, as you know, which compresses that blob of air. When it compresses, it warms. When it warms, it gets drier. Remember your temperature, relative humidity, and dew point effects. And when you take and compress that air and it gets warmer and drier, that's called adiabatic heating. And that adiabatic heating causes 60-mile-an-hour hot, dry winds to blow across the valley floor on the other side of the mountain range. And that, if you have a forest fire or brush fire burning, becomes a nightmare because we have these extremely high speed winds that are both hot and dry, drying out the fuels and raising total havoc to our fire environment. And sometimes they can be sustained for upwards of 2, 3, 4 days before this system finally breaks and moves out. And as you can see on the map here, there are a variety of different areas around the western U.S. that we can experience these föhn winds. And they are something that we need to be able to predict and work around. And that's why, again, IMETs are so valuable to me as a fire behavior analyst. Okay, extreme fire behavior, thunderstorms. Thunderstorms are a really big deal to us because we get two things, most importantly, lightning and winds. And that's why we take a look at it. Three things you need to create a thunderstorm. Lifting mechanism, that could be like solar radiation heating the Earth's surface, or a cold front. It requires an unstable atmosphere, and it requires moisture. If you have all three of those things, the warm blob of air rising in cooler air hits the dew point, the water vapor becomes visible. If it continues to go visible or vertical, it's going to condense those water droplets, which fall out. As those water droplets fall out, they create downdrafts. So what were in drafts vertically into the cloud now become downdrafts, and we now have outflow winds. Interesting things, we do not always get rain from thunderstorms. Sometimes what we'll get is what's called virga, rain that never reaches the ground. But what does reach the ground are those outflow winds. So even if the water evaporates and you see virga, you don't want to be flying under those clouds if you see virga, and we sure as heck don't want to be directly under it when there's a forest fire burning, because when those winds hit the ground, they blow the fire out in all directions and make a huge mess. So the three stages of a thunderstorm. Updraft stage, you can feel the wind whistling past your ears if you're facing the cloud, see the vertical development of the cloud. And then you hit this little moment where we call it, you can hear the birds chirp, because there's this reversal of wind direction. What was inflow now starts to become outflow winds, and this is when it's the most dangerous point. We have both inflow and outflow winds, and these outflow downdraft winds can be upwards of 60 miles per hour. Associated with it, we get lightning. Believe it or not, we've killed more firefighters with lightning than we have with burnovers and entrapments. Lightning is a dangerous factor out on the fire line. And when we start seeing thunderstorm development, we disengage from the fire and we go someplace safe so that we're not sitting on a ridge top or something and exposed to the lightning. Finally, the downdraft stage, we may stop the rain and we may still get downdrafts, which is still going to influence and affect our fire spread. Okay, thunderstorm winds, just kind of a quick idea. We have the indraft winds on one side, outflow winds on the other side, and it creates this gust front where the outflow winds hit the ground. And you can see where in this graphic here, it creates this curling of the wind and outflow. And a couple of meteorologists in the National Weather Service actually gave me a little mini lesson on the Doppler radar on how to recognize that. Absolutely fascinating. I could spot this on radar now when I'm watching and monitoring a fire if I don't have an INET with me. And then finally, this is what it would look like if you chopped off the top of the cloud and looked down vertically. Here's your indrafts at the back. Here's your outflow winds in the front. Now imagine this passing over a forest fire. There's no way to predict where it's going to go, how fast it's going to spread, what other kind of activity. This just screws with us so big time that all we can do is just disengage, get out of the way, let Mother Nature take its course, and then when things settle down, then we can re-engage. Thunderstorms are a really big deal for us in the wildland community. So in summary, lightning, outflow winds, turbulent gusts, poor visibility, and of course wind shear. Firefighter that was in one of my wildland classes shared this picture with me out of Arizona. You can see the outflow rain, Virgo over here, and you can see the outflow winds in the gust front. Isn't that amazing? What a beautiful picture. I love watching the weather. Anyway, what is plume-dominated fire behavior? Well, plume-dominated is nothing more than a thunderstorm created by the fire itself. The three things that we need to create a thunderstorm: unstable atmosphere, water vapor, and a lifting mechanism. Well, when you burn wood and cellulose material, it produces carbon dioxide and water vapor. So there's our water source. Where do we get the lifting mechanism? The heat of the fire itself literally superheats the air, and it wants to go vertical. And now if you combine that with an unstable atmosphere, an atmosphere that wants to make things go vertical, well, guess what? I got all three things I need to create a thunderstorm. So if you look at these pictures, what's really amazing about it is that it now is controlling the fire environment. The fire controls the environment as compared to a wind event. This thing down here is creating its own thunderstorm right on top of it. Right here at this level in the right-hand picture is very clear where the water vapor starts becoming visible. That's where the temperature just hit the dew point. Now, as it continues to go vertical, it's now forming water droplets. Those water droplets are going to fall out and come back down. So we had in-draft winds into the base of this smoke column, and then it reverses, and now we have outflow winds just like a thunderstorm, and it blows our fire all over Hellendown. It makes such a mess, and it'll do this multiple times in one day. And you start seeing this, that when you see these pyrocumulus clouds on top, those pyrocumulus clouds indicate a probable wind shift when the column collapses, and that's a real big deal for us to watch. Here's a beautiful one. This is a car fire a couple of years ago. This thing went to 32,000 feet. There's our dew point. Look at the turbulence and the intensity of the burning down here in the smoke. And then look at what it did when it hit the dew point, all that water vapor condensing into visible cloud. And it's punching vertically so hard and so energetically. Look at these shockwave clouds it's creating. Isn't that amazing? I mean, it was really bad for everybody whose houses burned up. But you look at this phenomenon and you sit there and you go, wow, how cool is that? That is just amazing. Mother Nature just blows me away sometimes. Anyway, another one. I don't know who put the soundtrack to this. This is looking westbound fire in Southern California. We had northerly winds pushing the fire to the south, and you can see where the mixing layer is at the top of the cloud layer. The winds out of the north, we had hot solar radiation, and up to the mixing height, very unstable atmosphere. And the fire, as it started progressing through the course of the day, was getting hotter and hotter. And pretty soon we started moving into convective enhancement at those lower altitudes. And you can see some mild plume-dominated activity. Of course, it got capped off by the mixing layer. Now, where would you want to fly? Below or above the mixing layer? Probably a little smoother air above the mixing layer. And you don't want to be anywhere near this fire when you're flying. But you can see how those columns have developed and then collapsed, and it would reverse the wind flow down at the Earth's surface and really mess with fire spread. Trying to do direct attack on a fire like that is just impossible. Now, later in the day, what's really cool is we've got a 90-degree wind shift, and it started getting an onshore breeze in Southern California that started reversing or causing a 90-degree wind shift in the fire spread, and you can see the smoke spreading towards the east where the camera's mounted, and it ended up causing that entire eastern flank of the fire to pick up and run like crazy. It was a big acreage gain that day. Okay, fire whirls are low-level atmospheric instability, only it's in the fire perimeter. The fire is producing its own vertical instability, and if you have an unstable lower atmosphere, then you're going to get things like fire whirls. They can be small, like this one, 5 feet in diameter, maybe 30 to 50 feet high, or you can get them a little bit bigger. And if you look at this one, you figure these are 100 to 150 foot tall trees. That is pretty dramatic burning in that fire. And look at how rapidly the smoke is being drawn into that base of that fire and the intensity of that burning. And it's self-propagating because that conservation of angular momentum as the inflowing air comes in. And as long as there's fuel burning, it continues to maintain this burning column of combusting air. Really, really amazing. So fire whirls are a really big, very scary to us. And those are things that we don't want to be anywhere near. Here's another one that was up in Minnesota. That was about 4 years ago. A friend of mine was on the fire, recorded this. And as you can see, it started getting pretty intense right at the Earth's surface. And it's literally drawing water up from this lake next to it. The intensity of the burning is so strong. It's that vertical lifting. You can see it lifting the water. And this one over here is turning into, from some fire whirls, it's literally turning into a plume-dominated fire. These are the kinds of fires you don't want to be anywhere near. This one on the right is just absolutely crazy. Dangerous, and we don't want to be anywhere near it. Okay, spot fires. What's a spot fire? It's a burning ember that goes outside the main fire line and lights a new fire somewhere else. We need three things for it to work. We need the firebrand source, we need the method of transport, and we need receptive fuels where the embers land. Firebrand sources, different kinds of vegetation produce different kinds of embers. They can either burn out really fast or burn for a long time. Some of them are literally aerodynamic, like bark plates and certain fronds of plants, and they can be continuing to burn and be locked up because of their aerodynamic shape and travel a long distance, and those are the ones that give us long-range spotting. Transport mechanism, I refer to it in technical terms of up, out, and down. Up is the vertical smoke column. Out is anything wind-driven. And down is gravity. If we have a mid-slope fire on a hillside, what we call underslung line, there's unburned fuel below, burning above, something burning in the black rolls out and goes down into the unburned fuel. Now it wants to burn back up slope again. And if we're mid-slope trying to fight the fire on that unslung line, we now have fire on both sides of it. It's not a good thing. And then finally, the receptive environment. The embers land in a parking lot, it ain't going to burn. But if you got receptive fuels, it could start a spot fire. One of the things that we can literally calculate is the probability of ignition, or PIG, and we calculate the probability of ignition to determine how likely we will get spot fires from viable embers. There's several environmental conditions that play into that. Well, that's my job as a fire behavior analyst, to assess those conditions and determine if we're going to get those spot fires. Short-range spotting is mostly wind-driven. Embers that burn out quickly but can be wind-driven horizontally. On the right, you can see the smoke column. This was back in the 80s when Yellowstone burned. Again, plume-dominated fire, ice cap on top, or pyrocumulus, and it lofted embers that went as far as 15-mile long-range spotting. Now, the conditions that are conducive to creating this kind of fire environment are the same conditions that can create one heck of a lousy ride in an airplane. So we want to recognize atmospheric stability and wind conditions that could affect our flying just as much as the effect it has on fighting fire. So crown fire is another thing we're concerned with. One or two trees, passive crown fire. It's not going anywhere. If you have active surface fire in the understory and crown fire above it, we call that active or dependent crown fire. But if you've got winds and a closed canopy and the fire is running through the crown, independent of the surface fire, well, now you know where it gets its name. Here's an example of single tree torching on the left. That was a fire I was on in Northern California. And this is group tree torching, another fire I was on, which doesn't go anywhere because there's no real wind and an open canopy. There's not a lot of trees around. But this is active or dependent crown fire. You can see the fire on the surface underneath the trees, propagating the fire in the crown. But this one is independent crown fire. It's got a good wind behind it. The fire is literally basically burning through a brush field 100 feet off the ground. As it burns through the aerial foliage, it's burning through the crown independently of any surface fire. And it's being wind-driven and fueled by a closed canopy, a tight, closed forest. And what causes that? 100 years of Smokey the Bear's 100% suppression policy. We now have forests that are choked to death with overgrowth. Fire is a natural part of the environment. And now we have fires like this because of our 100% suppression policy. So, in summary, how does a fire behavior do one's job? Well, very much like meteorologists. I have my own personal crystal ball. It's a little one. It's only 1.5 inches in diameter. It's portable, you understand. I've got my 8-ball, and I even have a pocket Ouija board on a keychain. Tarot cards, how do you predict the future without tarot cards? Flaming dice. Of course, I'm from Nevada. And one thing that I need to add to my kit, I need to get a satchel with chicken bones. I haven't learned that tool yet. You know, new modern technology, I need to try that. And finally, the weather rock. I think most everybody knows this. Weather rock's a very valuable tool. And this applies to pilots just as much as us fire behavior analysts. If you can see the rock, it's daytime. If it's wet, guess what? It's raining. If it's white, it's snowing. If it's moving back and forth, the wind's blowing. And if it's jumping up and down, earthquake. And when things get really bad out on a forest fire and we have to disengage, move back, and wait for conditions to get better, this is what we refer to as when things go gunny sack. When things go gunny sack, we sit back, light our incense, and chant our mantra, Om, and we wait for conditions to get back to where we can actually fight the fire again. Another tool that we use as fire behavior analysts and IMETs are weather stations that we can put in place where we need them. This is the old version. Down in Washoe Valley, we had a fire there a few years back. This is the newer version when I was on a fire down in the Pine Fire in Southern California 3 years ago. And this newer system is pretty sophisticated, transmits to satellites in orbit, which then transmit back down to us, and we can get the weather on the internet. It also has a transmitter in it that you just key up your portable radio, and it'll talk to you and give you the weather from anywhere out on the fire if you're within line of sight. Amazing technology, and we use them all the time. So, in summary, a little bit about aviation firefighting, just kind of for fun and kicks and giggles. We used to have older type World War II vintage aircraft, PC-6s and 7s, C-117 flying boxcars, excuse me, this one's incorrect. This is a P3 Orion. This is not a P2V Neptune. P2V Neptunes had 2 radial engines and 2 jet engines. We started moving away from those because they were getting so old and so high hours on the airframes, we were crashing them. So we started moving away from those and moving into more modern aircraft. Turbine engines like the P3 Orion and jet engines, as you can see on all of these. The Grumman S2 used to have 2 radial engines. This was a anti-submarine aircraft used by the Navy. Now CAL FIRE and a couple of other agencies use them, and they've converted them to turbine engines instead of the old piston engines. They can carry 1,200 gallons of retardant. P3 Orion carry 2,000. The BA-146, 3,000 gallons. And then, of course, we get the very large air tankers, or VLATs, like the DC-10, the MD-80, and the 747. And those can carry 11,000. The 747, I think, carries 14,000 gallons of retardant. Here's an example of a twin-engine Type 2 air tanker dropping on a fire I was on in Jackson Canyon, Casper, Wyoming. Lead plane out in front. They fly in front. They hit smoke and do a little smoke streamer and show exactly where they want the air tanker to make the drop. And so they work in tandem, lead plane and air tanker. This one down here is really cool because it can literally land on a road, be refilled by a water tender or a portable batch plant for retardant, and can haul up to 800 gallons. This is my ultimate fantasy. Combine my firefighting years with my passion for aviation, boy, would that be the final retirement job for me. Helicopters, we use a lot of helicopters. Bell Jet Ranger, this is a fire up in Idaho. See that guy there? That's me. See the other guy? Hey, that's me too. Actually, I was the guy that took the picture. They flew me up to the helispot, dropped me out, hauled my gear down to me so I could go hike the fire line for the day. We can use these light helicopters like the 407 and the 206 for bucket drops, but they only haul 50, 75 gallons of water. So they're really pretty useless. We use them more for recon flights, and that's where I spent most of my time. So I go out and watch the fire a lot from the air. This is where on the lower right, we're using Aerospatiale Llama for recon, looking for hot spots with an infrared camera. But for actual firefighting, Type 2 and Type 3 helicopters, the Blackhawk's a Type 2, Bell Hueys, you're probably familiar with, the UH-1 Hueys, those are Type 2 helicopters. And then we have the Type 1s, the K-Max, the Chinook, and the Sky Crane. And those can haul a couple of 1,000 gallons of water or retardant, which is really pretty amazing. Here's the Sky Crane, another fire I was on up in Idaho. I went down to the fill area where they had the batch plant, and then later I was out hiking the line and caught this picture here of the air tanker dropping and a little ND500 with the Helico, the helicopter coordinator directing the helicopter firefighting operations way up here on the right. Now, how do we organize everybody on a fire? Down lowest altitudes, we have the helicopters. And because helicopter PICs are in the right seat, they generally orbit clockwise until they're ready to drop. Fixed-wing aircraft like air tankers, lead planes, and seats, because the pilot's in the left seat, they orbit counterclockwise until they're directed into the fire and make a drop. All of that is coordinated. The helicopters are coordinated with what's called a HELCO, or helicopter coordinator, who sits above and watches them all. And then we have air attack. They sit 3,000 or 4,000 feet above everybody, and they watch the overall firefighting operation. There's a pilot and an air attack group supervisor. The ATGS is the guy in the right seat, so the airplane's got to orbit clockwise, so the ATGS can look out the window and watch what's going on. And the air attack then directs all of these aircraft as to how to coordinate and attack the fire. And sometimes we can get 7, 8 helicopters, 4 or 5 air tankers, all kinds of things going on all at once, and it gets pretty crowded. Smoke jumpers are a unique tool. They jump out of a fixed wing. A stick of jumpers is anywhere from 2 to 10, and those guys are great for initial attack. If the fire goes beyond initial attack, most jumpers are qualified for incident management duties until we take it over with an incident management team. But we like to tease smoke jumpers. There's only 2 things that fall from the sky: skydivers and bird poop. But they take it all in stride. They're actually a very valuable tool in the firefighting community. Now, one more thing that we're concerned with as pilots is weight turbulence. Well, guess what? As firefighters, we're a little concerned with that as well. Here's a DC-10 dropping on a fire in Southern California. Watch the smoke right about where the guy drops his retardant, and you can see the downflow of his weight turbulence. As you guys know, heavy, slow, and low, and where you're going to get your worst weight turbulence. And it's those kinds of activities that are going to create the weight turbulence both along our fire edge and as we're trying to land behind one at an airport. So big, heavy airplanes like that can be just as much of a problem to us firefighters as it is dangerous to us pilots at an airport, particularly when you're doing parallel operations like Reno Airport. Helicopters, again, can be a problem. These Sky Cranes and the Chinooks, they shove so much air downwards that sometimes they fan the flames, and they're more problem than they are fighting the fire. So we have to really kind of take into account how we apply these aircraft because of the rotor wash and the wake turbulence they create. So anyway, that's all I have for today. I hope I kept it within my time limits. Again, there's my fantasy. Could you imagine that? An 802 air tractor, air tanker on floats and fly it out of Fort Wainwright in Alaska. That's where I took this picture. Just a beautiful, beautiful aircraft. It was so amazing. Anyway, maybe I'm going to be a future air tanker pilot. Maybe I'll just retire and go fly kids for young eagles. Anyway, it was a pleasure. I hope you guys got something out of it. Thanks for your time.
Awesome. Thank you so much, Sandy. We appreciate you as always. Got to say, we enjoy that picture of the dog there with the little airplane wing costume on. I've actually known Sandy for, probably about 14 years now, give or take.
Yeah,
We met
exactly.
back when I worked up in Boise, and he has been a great resource to have help present at IWAWS, and we do appreciate it. Sarah, it looks like you chimed in there, so I will pass it on over to you.
Alrighty, this concludes our IWAWS 2020 virtual experiment adventure. Something we've been talking about the team is this has been a tremendous undertaking, to say the least. We started out with budget challenges and limitations and who could present and how everything could happen, and kept rearranging, and then gradually COVID came in, and then we're figuring out, all right, when do we need to make the decision to go virtual? How is this going to impact travel? How is this going to work? And through it, we had a lot of people step up and say, yeah, let's keep trying it. Let's not give it up. With that, we did a full 2-day completely virtual workshop with around 20 presenters. We had presenters extending from the East Coast, started us off yesterday morning, to the West Coast. Multiple time zones for presenters. We've had numerous IT challenges, but you know what? We've been exceptionally grateful for everyone's patience, not only the speakers and how they've been willing to work with us, but also those who are attendees sticking with us when I promise we were just as frustrated as you were with all of this. Again, I do want to thank all of our team members. Just a quick listing of those. Katie Branham, our co-chair, who is coming off of MIDS, and even though knew when she was early on that she wasn't going to be able to do the travel part, stuck with us and has spent a lot of long hours with that. Don Johnson for originally doing all the legwork in Reno, and then transitioning to this, and as you've heard her with all of our tech problems, okay, we'll keep going. So for everyone else of the team, Shar, who's been doing all of our social media work and has been here with me in the building as well. Going to Steph and Jane, new members of our team who have, learned a great deal, and I think we will be, continuing that relationship and keeping that new blood coming in. Don't think Jason was able to join us for most of the workshop, being, new dad. We had Jason. Ken is off shift for the afternoon. And then, of course, Scott and Brian as our advisors and mentors in this process as well, and handling a lot of the bigger scale, unique aspects of presenting a conference. So thank you all, especially the presenters, East Coast all the way out. We had a total of 250 people registered for this workshop, extending from Spain to Hawaii, which is more than we could have imagined, especially as this went virtual. So thank you all so very much. Don't forget for pilots, we do have that wings credited in the chat, so please go through there. If you have any problems, reach out to us, and we will do our best to get that information, coordinate you with the right person. So thank you all again. We greatly appreciate you sticking with us and your time and dedication and interest in aviation. And for all of you that are pilots, please stay flying and stay safe. Thank you all very much. This wraps up IWAWS Virtual 2020.
Jade, it looks like you requested to show us something. All right, I see that viewer 137 had a question about SBM positions out of Utah. Sandy said you can go ahead and email him, and we will have all that contact information out as well. Once again, thank you, everybody. We are signing out of the meeting now. Oh, thank you very much, Sandy. So for 137, Sandy's information is at the bottom there. It's sbansandy@gmail.com. Thank you, everybody. Have a great rest of your weekend.
And we'll be getting this information to our website as soon as we can, getting all those presentations uploaded.